Hi and welcome to the lecture on deadlocks. After watching this video, you will be able to define what is a deadlock, its characteristics, and an illustration of the dining philosopher's problem and the necessary conditions for deadlock. A deadlock is a situation where there is no progress and waiting time is infinite. In an operating system, deadlock occurs when a process or thread enters a waiting state because a resource requested by it is held by another waiting process, which in turn is waiting for another resource held by another waiting process. As we can see in this figure, task 1 needs the scanner to complete, while task 2 needs the printer to complete. Task 1 is holding the printer and is waiting for the scanner, while task 2 is holding the scanner and waiting for the printer. Task 1 can complete only when task 2 completes and releases the scanner, while task 2 can complete only when task 1 completes and releases the printer. So both the tasks are waiting for each other infinitely. This is a situation of a deadlock. Can we see deadlocks in our real life? Well, most of us would have heard the story of two goats trying to cross a narrow bridge over a river, each one from either side of the bridge. As you can see, none of the goats can reach the bank unless one decides to go back. Another example which we see often is a traffic jam. Here we can see all the vehicles jammed and none of the vehicle can move unless someone intervenes and moves back some of the vehicles. Let us now consider the dining philosopher's problem, which illustrates the deadlock situation. Here we have 5 philosophers sitting around a dining table. 5 bowls of noodles is placed before them along with 5 chopsticks. The philosopher does only 2 things. They think, which is independent of each other, and when they are hungry, they eat. To eat, they pick up the chopstick on the left and then pick up the chopstick on the right. And then, once they have both the chopsticks in their hands, they start eating. Once they finish eating, they put down the chopsticks and then go back to thinking. So here we can see the sequence in which the philosophers act. They think, and when they are hungry, they pick up the left chopstick and then they pick up the right chopstick. Then they start eating once they have both. Then after eating, they put down the chopsticks and go back to thinking again. So far so good. There is no problem if 1 or 2 philosophers feels hungry simultaneously. But consider a situation where all 5 of them are hungry simultaneously. Each one of them would pick up the chopstick on their left at the same time, and they will be waiting to get hold of the chopstick on the right. But as you can see, there are no chopsticks left on the table, so they have no resource to pick up. So each philosopher will be waiting for the next philosopher to finish eating and put down the chopstick so that they can start eating. But none of these philosophers is going to put down the chopstick because none of them have the second one. So this is a situation where each one holds a resource and is waiting for another resource. As you can see from this picture, 4 points are evident from this. First one is each of them picked up the chopstick, and when one chopstick, single philosopher could pick up only one chopstick. That is, here we have a mutual exclusion. That is, when a philosopher picks up the chopstick, no other philosopher competes for it. The second thing, each philosopher is holding the left chopstick in his hand and waiting for the right. That is, there is a situation of hold and wait. The third one, The chopstick cannot be snatched away from the philosopher's hand. This is referred to as no preemption. And the last but the most important one, each one is waiting for the next philosopher to put down the chopstick. The first one is waiting for the second for the third for the fourth is waiting for the fifth philosopher, and the fifth one is in turn waiting for the first, which forms a cycle. Thus, the four necessary conditions for deadlock to occur are these. 1. Mutual exclusion. That is, only one process can use a resource at a time. The second condition is hold and wait. A process may hold allocated resources while it is waiting for other. No preemption. A process can release a resource only voluntarily. And the last but the most important, a resource, there is a closed chain of processes where each process holds at least one resource needed by the next process in chain. Now, how do we prevent these deadlocks? There are 3 strategies adopted to prevent deadlocks. The first one is prevention. We all immunize our kids, and we all were immunized when we were kids, in order to safeguard us from certain deadly diseases. So that is prevention. So we can follow the strategy by disallowing any one of the 4 conditions to exist. By making sure that 4 conditions do not become true at the same time, we can prevent deadlock. But this kind of a measure is very ineffective because it leads to the inefficient use of the resources. The second method we have is avoidance. As we can see on our roads without signals, during the peak hours we can find a traffic police standing, while during the ordinary hours there is no police on the road. That is, we sense the time when there is a heavy traffic flow and there is a chance of a deadlock, and then we start avoiding it. So that is the strategy we follow. As long as the system is in the safe state, we are going to continue without any problem. Once we detect that the system is going into an unsafe state, we step in and avoid this situation which causes deadlock. The third strategy is to let the system behave as it wishes, and once we detect a deadlock, let us step in and then recover. In the next video, we will see in detail about all these deadlock handling mechanisms. Thank you.